Functions with percent change. In this video, you'll learn how to write a numerical expression or algebraic expression to represent the result of applying a percent increase repeatedly. A percent increase means multiplying by a number greater than 1. To convert a percent increase into a multiplication factor, we add the decimal value of the percent to 1. So if we have a 10% increase, then we'll turn the 10% into a decimal of 0.10 and add 1 to it. So the multiplication factor will be 1.10. A percent decrease means multiplying by a number less than 1. So to convert a percent decrease into a multiplication factor, we subtract the decimal value of the percent from 1. So if we have a 15% decrease, then we'll turn the percent into a decimal of 0.15 and subtract that from 1. So we'll have a multiplication factor of 0.85. Let's look at some examples of these percent changes. To get a new computer, a recent college graduate obtains a loan of $450. She agrees to pay 18% annual interest, which will apply to any money she owes. She makes no payments during the first year. So how much will she owe at the end of 1 year? We know that she agrees to pay 18%. So we're going to turn the 18% into a decimal of 0.18. And we'll add it to 1 since it's going to increase. This will give us the multiplication factor of 1.18. So we can take the loan of $450 and we'll multiply that by our multiplication factor of 1.18. This will give us a value of $531 that she'll owe after 1 year. Now how much will she owe at the end of 2 years? So we'll take the loan amount of $450 and the multiplication factor of 1.18. But we're going to add an exponent of 2 since now we have 2 years. Squaring 1.18 gives us a value of 1.3924, and multiplying that by the 450 will give us a value of $626.58 after 2 years. Now let's create an equation to represent the amount she owes at the end of x years. So we'll take our exponential function, where a is the initial amount, which in our case is 450, and b is our multiplication factor, which in this example was 1.18. In this example, Lynn bought a new TV 5 years ago for $1,200 and wants to resell it. She learned that it depreciated in value by 15% every year. How much is her TV worth now after 5 years? So let's start by making an equation for this situation. We know that she bought the TV 5 years ago for $1,200. So we'll replace A with the $1,200 of the initial amount. And we know that it depreciated in value by 15%. So we're going to subtract the 0.15 from 1 since it's decreasing. This gives us a multiplication factor of 0.85. Now that we want to know how much it's worth after 5 years, we'll replace x with 5. Multiplying 0.85 by itself 5 times will give us a value of 0.4437, and then multiplying that by the original amount of $1,200 will give us a value of $532.45. So that's how much Lynn should sell her TV for now after 5 years. In this example, we're going to complete a table that represents 2 loan companies and their interest rates if they loan $1,000. The first column has a loan balance of 5%, and the second column has a loan balance of 8%. And then our rows are broken up into 1 year, 2 years, and then T years. So let's start with 1,000 times 1.05, which represents the principal of the amount times the 5% that we're adding. This gives us $1,050 after multiplying those. For 2 years, we'll start with the same expression, but now our exponent will be 2. 1.05 squared will give us 1.1025, and multiplying that by the original amount of 1,000 will give us a value of $1,102.50. To represent T years, this tells us that we can find the value after any amount of years given, so we'll just leave the variable T. Now let's look at the loan balance of 8%. So we'll multiply our principal of 1,000 times 1.08, since 8% is being increased. Multiplying them together gives us a value of $1,080. Now let's look at 2 years. So we'll start with the same expression, but our exponent will be 2. 1.08 squared gives us a value of 1.1664, and multiplying that by the $1,000 gives us a value of $1,166.40. So our equation after t years will have the same expression but with an exponent of t. In 2011, the population of deer in a forest was 650. If the deer population continues to increase by 15% each year, write an expression that represents the population after t years from 2011. So we'll start with our exponential function, where we know that a is the initial amount and b is our growth factor. We know that the population of deer in 2011 was 650, so this will be our a value. And we know that it's increasing by 15% each year. So we'll add the decimal version of 15% to 1 since it's increasing. This gives us a multiplication factor of 1.15. So now we have an exponential function for this situation. In our last example, we're going to create an exponential equation from each situation. The first situation says that for an experiment, a scientist starts with 2,500 insects and predicts that the number of insects will decrease by 14% each week. So we'll take our exponential function, and we can see that a, our starting point, was 2,500, and since it's decreasing by 14%, we'll subtract 0.14 from 1. This gives us a value of 0.86. Now we have an equation for this situation. This one says that a famous YouTuber discovered that when she uploads videos, the viewers increase by 13% each hour. There were only 2 viewers at the time of upload. So we'll take our function, and we can see that a is our initial value of 2 viewers, and b is our growth rate. So we'll take the 13% and add it to 1. So we get a factor of 1.13. Our last one says a pharmacist told her patient the amount of medicine in her body will decrease by 5% each hour. She started with 400 milligrams in her body. So if we take our equation and a is our starting point, then we'll replace it with the 400 milligrams. We know that it's decreasing by 5%, so we'll subtract 5% as a decimal of 0.05 from 1, which will give us a factor of 0.95. Now let's recap what we've learned. Exponential equations model situations where a quantity increases or decreases by a consistent percentage over equal time intervals. And we use the formula y equals a times b to the x power, where a is the initial value and b is the rate of change. X represents the time intervals.